All right, so let's recap what we talked about yesterday for Chapter 5. We didn't get very far in the notes yesterday on Chapter 5, but we did talk about a whole lot of stuff. And the first thing that we talked about is that Chapter 5 deals with continuous random variables, and that the topics that we talk about in Chapter 5 are extremely important. In my opinion, Chapter 5 is one of the most, or if not the most important chapter for your success in this class, because every single thing that we're going to do after Chapter 5 builds directly on the concepts that we learned in Chapter 5. So Chapter 6, Chapter 7, Chapter 8, and Chapter 9 all make heavy use of everything that we learned in Chapter 5. Chapter 10 doesn't, for this class at least, doesn't use a whole lot of stuff that we're going to cover in Chapter 5. But the theory behind Chapter 10 does, but we're not going to really get too heavy into the theory in Chapter 10. Chapter 10 deals with regression analysis, and there's a whole class here at UNCC where that only specifically focus on regression analysis. So we're just going to introduce that topic, and if you're interested in regression analysis, then you can take that course, which I highly recommend. Regression analysis is one of the most widely used concepts in the real world, whether it's in industry or if you stay in academia or if you go to graduate school or what have you. A lot of people use regression analysis. But let's first focus on Chapter 5 before we get too far into that conversation. So, Chapter 5 deals with continuous random variables, and what we said for continuous random variables is that now, whenever we look at their distributions, the distributions are always going to be some kind of smooth line. And what we're going to say that is if we try to contrast that with a discrete random variable where those individual values can just fall into buckets, obviously here these two graphs look a lot different, this one on the left and the one in the middle. But what we also then said yesterday is that if we wanted to find the area of some shaded region like we have right here between A and B, in particular if we wanted to try to do something like that for a smooth and continuous line like we have for the normal distribution, one of the questions that we can start asking ourselves is, unlike what we could do for the empirical rule where we had to go whole standard deviations either to the left or to the right of the mean, either above or below the mean. What we wanted to start talking about now is, what happens if we don't want to go a whole standard deviation? What happens if we only want to go a half of a standard deviation? That's when we got a little bit into the discussion of down here where I said, hey, if we just look at this 34% sliver, so between the mean and one standard deviation above the mean, if we just look at that 34% sliver that we got from the empirical rule, if instead of going a whole standard deviation above, we only want to go a half of a standard deviation above, I first asked you what your intuition told you about how much should be in this shaded sliver right here. And you said, well, if we're only going halfway up, then that should be half of the 34%. That's what your intuition told you. But then we saw that after we blew up that 34% sliver, and if we only went half of the standard deviation above, that this left-hand side definitely wasn't the same size as this right-hand side. So therefore, definitely this shouldn't be 17%. This should also not be 17%, right? So simply just taking the 34% and dividing it by 2, if we only go a half of a standard deviation above, we saw that that simply couldn't be correct, right? So we then asked ourselves, okay, if we can't just take 34% and divide it by 2, how could we figure that out then? And then that's when we started to look a little bit at our z-table, or our cumulative normal probability table. And what we said was we started here with the backside, which here I said that the side that only has a little bit shaded in, that's what I'm going to refer to as the backside. The side that has a lot shaded in, I said I was going to refer to as the front side. When we first started off with the backside, and we said that the way to read this table is that here we have this little z, and what that represents is that here in this first column, and here in this first row, those represents our z values. So if we wanted to look up a z value,
of, say, negative 1.37, I forget which ones we used yesterday, but I don't think it was 1.37, then the way that we would look up a z-value of negative 1.37 is we would first go down to the first decimal place, so here to negative 1.3. And then after we went down to the first decimal place, we would go to the second decimal place, and the second decimal place was in these columns here where we have 0.07. And where these two things meet up then, 0.0853. What that represents then is if we shade in our distribution from all the way down from negative infinity all the way up to a cutoff of a z-value of negative 1.37, then we will have shaded in approximately 0.0853, which is about 8.53%, right? So then what we said was in the body of this table, all these things are percentages, and these percentages represent the percentage of the distribution that we will have shaded in up until some z-value cutoff if we start shading in from the left. Right? Is everybody good with that so far? Then what we said is this is on the back side, and on the back side we had all negative z-values, so we're going to have z-values that are below the mean. But then if we come over here to the front side, here again we only have positive values. And again, like I said yesterday, here we're missing that first row. Right, so here we'll have 0.00, 0.01, 0.02, and all the way to 0.09. And then the same thing that we can do on the back side, we can also do on the front side. If we're looking up a positive z-value, we can find that positive z-value. But now since we have positive z-values, we're shading in our distribution somewhere above the average, so we're going to have positive z-values over here. And because we're shading in our distribution all the way to above the average, we're going to have shaded in at least 50% of the distribution. And that's why if you look at all these percentages in here, they're all going to be above 0.5. Right? The only one that's not above 0.5 is, what is the z-value of the mean? Zero, right? The z-value of the mean, if you're saying how far away is this thing from the mean, well, the mean is 0 away from the mean, 0 standard deviations away from the mean. So here if we go to 0.00, we have exactly 50%. Another way of saying that is if you shade in this distribution starting from the left all the way up to the mean, then you will have shaded in exactly 50% of the distribution, right? If you start from the left. And we're always going to shade in from the left, right? Good. So then the only other thing that we really talked about yesterday was we also talked about these different characteristics down here. The first one that we talked about is that this graph has to always be above the x-axis, right? Or less than, greater than, or equal to the x-axis. Right? So it can technically touch the x-axis, but it can never go below the x-axis, because we said if it goes below the x-axis, what that would really then represent is a negative probability. We said that we can't have negative probability, so we're always going to say above the x-axis. And then we also said that if we shade in everything underneath this graph, absolutely everything underneath this graph, then we'll have shaded in 100% of the distribution. And 100% of the distribution then means that we'll have shaded in an area of 1, right? So, any questions about any of the stuff that I've talked about so far? It's really just a recap of yesterday. All right, and then the last thing that we talked about was this definition right here for any continuous random variable x. We have that these 4 things are all equal. And then we started off this conversation by saying, hey, what's the difference between those 4 things? And then we recognize that here this one includes the equality sign, but this one does not in front of the a term. And then this one right here is missing it by the b term, and then this one is missing both of the equality signs. And basically what we went through then is we went through a discussion. I don't think that's on the back side of this page. But we went through a discussion about that 40-yard dash time. If I say, hey, go out to the track, you're going to meet this guy named Philip, and you're going to take his 40-yard dash time, right? You said it could be somewhere between like 3 and 7 seconds. And we said that there's going to be 100% probability that it's going to be between 3 and 7 seconds. But then if we cut that in half, and we said from 3 to 5 seconds, there's a 50% chance that Philip's 40-yard dash time is going to be in there. And there's going to be a 50% chance that it's going to be between 5 and 7 seconds. Right? I took that range and I just cut it in half. Right? And said it was equally likely, so both those sections had 50%. And then what we did was we kept subdividing that time into smaller and smaller and smaller segments. All the way to the point where I said, hey, what happens if we have this itsy-bitsy tiny little segment that the probability that Philip is going to run the 40-yard dash time in this tiny little section is only like 0.00001%. Right? Everybody remember that discussion from yesterday? And then I said, okay, let's take it a step further. What happens if I asked you, what's the probability that he's going to run that 40-yard dash time in exactly 4.57638.279 seconds, right? And if you think about that, if I ask you what's the probability that someone's going to run the 40-yard dash time in exactly that amount of time, well, the probability for that is 0, right? So then what we said is that if we choose one very specific value, then the probability of that one very specific value has a probability of 0. So therefore, if we are just subtracting out one value, right? Here we're including the value of A, but here on this one we're not including the value of A. We're just subtracting something that has the probability of 0. So therefore, if we're here we're looking at the probability of something, here we're looking at the probability of something, you can kind of think as this thing right here. I'm going to rewrite this. The probability of A is less than or equal to X is less than or equal to B is equal to the probability of A is less than X is less than or equal to B. So all I've done so far is rewrite these two things. But you can think of this as being plus the probability of A, just of A, right? So I'm taking it out of here and I'm just including it over there. But we said that the probability of exactly one value is equal to 0. So this is like adding and subtracting 0, or here it's just adding 0, right? So that's why we said the probability of these things right here are all the same because we're just subtracting out something that has a probability of 0. And that's kind of where we left off yesterday. And I said for all of this stuff right here, if out of all of that discussion that we did with like the whole 40-yard dash time and everything, if the only thing that you remember is this is equal to this, so it doesn't matter if we have the equal sign or don't have the equal sign. If that's the only thing that you remember, you're going to be fine for doing the problems in this class. Right? All that other stuff was a bit more of theoretical background that I at least want to present to you once. But if the only thing that you remember is, doesn't matter if there's equal signs or not equal signs, then you're going to be good to go. All right.
If there's an equal sign, because probability of it being equal to just that one would be 0.
Exactly. Because the only thing that's different between these two things is the equal, and that's just that one value being included or not included. Yep, exactly. All right, so that's where we left off. Let's go on to the next page. The next page, we're again going to get into a little bit of theoretical stuff. Not too much stuff, though. And then after that, we're going to get into a bunch of problems. All right. The probability distribution corresponding to the density function for a bell-shaped curve with parameter mu and sigma is called the normal distribution with mu and standard deviation sigma. All that is saying is that, and this is a term that I've introduced a couple of times before, if we have a bell-shaped and symmetric distribution, we can refer to that as the normal distribution. So this right here is doing a little bit more than that, but it's really just saying, hey, we can call this thing up here a normal distribution. A lot of times in the real world, we'll refer to this as the normal distribution, or Something else that you will hear a lot in the real world is that this is called the Gaussian distribution. Gaussian distribution. It's giving credit to a famous mathematician named Gauss. I don't know specifically if Gauss came up with this, but a very common practice in mathematics is whenever somebody comes up with something that is even vaguely and very remotely associated with something that a famous mathematician has done, they'll assign that mathematician's name to it so that people will buy into it a lot quicker, right? So it's kind of like me coming up with a new brand of tennis shoes and me putting the Jamaican flag on it, and then me saying that these are Usain's Bolt's type of tennis shoes, right? And then people are going to be like, cool, I'll buy those, right? And it has nothing to do with them whatsoever, right? So it's kind of like the same thing that's happening here. This is a normal distribution. I have no idea how much Gauss actually did with this, but a lot of people refer to this also as the Gaussian distribution. Exactly, right? It's like all these goofy, dorky mathematicians coming up with ideas and just like, no, I want to be popular too, assigning Gauss's name to it. All right. Then also here, a continuous random variable whose properties are described by the normal distribution with mean and standard deviation, sigma, is called a normally distributed random variable or a normal random variable. All that that's saying is this. All right. What we have is whenever we have a set of data, like a data set, one of the things that we've always done is that we've kind of listed out the outcomes that are associated with this data set, right? Let's go back to the easy example that we've done a couple of times so far, and that is of rolling a die, right? Let's say, for instance, that if we roll a die, we can get the numbers 1, 2, 3, 4, 5, or 6, right? Or if we want to write this in terms of our sample space, we could just simply just show it as 1, 2, 3, 4, 5, or 6. Well, let's say that it was a fair die. If it's a fair die, then if we roll this die 6 times, in an ideal world, what we might see is that each one of these values occurs once, right? That's a reasonable assumption for an outcome that we could see, right? Or a set of outcomes that we could see. What we're essentially saying here then is this. Let's say that this was not a fair die. Let's say that it was some kind of weighted die. And if you rolled this die a bunch of times, what you would start to get is a distribution that kind of starts to look like a bell-shaped curve. Right, is everybody good with this? Then what we're going to say then is that these random variables, which we always described as being our x values, right? Whenever we wanted to plug in an x value into those equations that we've been working with, we've always plugged in the values in our sample space, right? Does everybody remember that? If we're going to call these things our x values, and if these things are distributed like a normal distribution, then each one of these things right here are going to be called normal random variables, right? Because they're all random variables, but now these random variables are going to have a distribution like a normal distribution, so we're going to start calling them normal random variables, right? Again, not super important for you to remember for this class, but that terminology is important, especially if you decide to go on and take more statistics classes. All right, so then a density function for a normally distributed random variable with mean, mu, and standard deviation kind of looks like this, which we already kind of seen. But now what we're going to start talking about is what happens whenever we're changing sigma, our standard deviation. So whenever we start having a standard deviation, remember whenever we first started talking about standard deviations, again, what's the easiest way to wrap your head around what a standard deviation is? It's
just like a measurement of distance, right? So if something has a small standard deviation, then those things are packed together a lot more tightly. If something has a large standard deviation, those are a lot more spread apart, right? That's exactly what this is saying right here. All of these things are bell-shaped and symmetric curves. But the difference between all of these bell-shaped and symmetric curves is that here, these things are a lot tighter together. And if you compare that to these other ones down here, these are a lot more spread apart. They're all bell-shaped and symmetric. They're all normal distributions. But now we're just changing the standard deviation of all of these. Here we have a smaller standard deviation, so they're all packed together a lot more. Here we have a larger standard deviation, so they're all spread farther apart. So there's two things then that govern what our normal distribution is going to look like. One is where its center is. Here all of these are centered at the number 6. But the other thing that's going to determine what our normal distribution looks like is also going to be the standard deviation. So therefore, the two things that we always report whenever we're talking about a normal distribution is we always want to know what the mean is and what the standard deviation is. So therefore, we can get an idea of which kind of bell-shaped and symmetric distribution that we're looking at. Right? All right. Another way to write this then is whenever we're dealing with normal distributions, if we're interested in the parameters mu and sigma for the mean and the standard deviation, one way that we can write this then is that we're looking at a normal distribution with parameters mu and sigma. You're never going to see this notation really in any of the problems for this class. However, if you go on and you take additional statistics courses, you're going to run into something like this more frequently. Because what tends to happen in other statistics classes is we start to introduce a lot more other kinds of distributions, not just the normal distribution. So we're going to start to differentiate what those different distributions are. And we don't always want to write out normal distribution with mean this and standard deviation this. We don't want to write that entire sentence. So we just start including them as sentences. All right. But like I said, not knowing this notation for this class is absolutely no big deal whatsoever. All right. Now we get into some of the fun stuff. We're going to get into doing some of the problems. Before we get into some of these problems, one of the things that right here I want to make sure that I point out, the difference between a normal random variable and a standard normal random variable. The way that we get from a normal distribution or from a normal random variable to a standard normal random variable, the only thing that we have to do is we have to standardize this somehow. What we're talking about standardizing is we're doing this. We're essentially converting an x value to a z value. Right? We're converting an x value to a z value. That's essentially what it means with standardizing stuff. Because whenever we have a z value, the reason why we want to convert stuff to a z value, what would be one big benefit of converting stuff to a z value? Yeah, you can use the chart, right? Like that chart gives us a whole lot of information. We can use that chart to figure out what percentage of the distribution we have between some arbitrary cutoffs, not just whole standard deviations, but now fractions of a standard deviation. So if we want to use that chart, we have to know the z value. So therefore, if we have some x value, if I said, hey, what's the probability that a student that you pick at random from UNCC is going to have a height of less than 5 feet 6 inches, right? Right now you have no idea. But if I told you that the heights are normally distributed, now you can say, all right, well, if I know that it's 5 feet 6 inches, that's my cutoff, and I want to know what percentage of people are below my cutoff. If I know the z value to that cutoff, now I can look it up in my table and I can tell you that So one of the things that we're going to keep doing from now until the end of the semester, we're going to do this probably about 5,000 times, is we're going to keep converting x values to z values, right? So what this process is we're standardizing our x value, standardizing it because we're always going to go back to that one table. It's just a standard process that we're going to follow. And what we're basically doing is we're changing our normal distribution, like we had on the other page where we can have a whole bunch of different curves, to just one curve, the same curve that we're using in our table. Right? So let me ask you this.
How do you convert an x value to a z value? How do you convert an x value to a z value?
Awesome.
Right? You guys are both saying it. If you have some x value, if you subtract the mean from it, mu, and you divide that thing by the standard deviation, well, now you've just taken that x value and you've converted it into a z value, right?
So what we're going to keep doing is we're going to keep getting x values. Like, hey, you have a cutoff of 5 feet 6 inches. That's not telling you a whole lot. If I can convert 5 feet 6 inches into a z value, I can look it up in my table. So then we're going to keep coming back. We're going to take 5 feet 6 inches. We're going to subtract the average height from it and the standard deviation of height. And we'll have converted 5 feet 6 inches to a z, and we can go look it up in our table. Right? You guys starting to see why knowing this formula I said was extremely, extremely, extremely important. When we first looked at this formula, I said, hey, if you don't memorize any of the formulas, I'm fine with that. But if there's one formula that you're going to remember or should remember, it should definitely be this one right here, because we're going to use this one a whole lot. We're going to keep making small changes to this formula, but essentially we can always boil it right back down to this formula. All right. Then if we standardize this, or if we take some x and we convert it to a z value, now we only have one normal distribution, and that's where the mean is 0 and the standard deviation is 1, which is simply just called a standard normal distribution. All right. Everybody good with this? So our overall objective is always going to be, like for a lot of the stuff that we do from here until the end of the semester, is converting something to a z value. And once we get to a z value, we're just going to come right back to this table, right? Which is why I wanted to introduce this table to you before I introduce that other table for the binomial distribution, because everything that we're going to do for the rest of the semester is always going to make use of this table. So let's do it. We have a whole bunch of examples to practice this with now. Examples using the standard normal distribution. Let's say that you want to find the probability
that z is less than or equal to 1.48. So let's first draw a picture, right? If we want to find the probability that z is less than 1.48, what we're saying here is this. First question that you have to ask yourself whenever you're doing these problems. So one of the things that I like to do in my class is I like to give you guys a certain steps to always follow. And if you guys always follow these steps for these types of problems, chances are you're going to get these problems right? So the steps that we're going to follow for these problems, the first thing that we're always going to ask ourselves is this right here a z value? Well, it is a z value. So if we're looking at z values, we know that we're going to look at our normal distribution, our standard normal distribution, a bell-shaped and symmetric curve. So the first question always is, do we have a z value? Yes, we do have a z value. All right, let's draw ourselves a picture that looks like this. Now we have some cutoff, and that cutoff is the value of 1.48. So a z value of 1.48. Is that above the mean or below the mean? Above the mean. So here we have some cutoff, that's 1.48. All right, are we looking to be greater than 1.48 or less than 1.48? Less than 1.48. So therefore, we're looking for this shaded region of our graph right here. Is everybody good with that? If I said, hey, tell me the percentage or the probability of this shaded region, what would you do?
So 1.48 as my
not plug in 1.48 as your x. Look at the table, right? You look at the table. So we have a z value that's 1.48. Right? This is a z value equal to 1.48. That's our cutoff. And if we have a z value of 1.48, now we're going to go to our table. We've done this a couple times now, so I'm going to have you guys walk me through. We're looking for a z value of 1.48. What do I do?
You're going to do 1.4 on Z,
Find 1.4?
and then you're going to go to 0.08.
Awesome. 0.08, which should be this one right here, as long as I'm lining this stuff up right. Right? So you guys get this value too? 0.9306. All right. So 0.9306. We get from our table 0.9306. Right? Is everybody good at how to get that? So our first, oops, let me make sure you guys can see that. So our first step was, are we dealing with a z? The answer to that is yes. So therefore, we're going to use our normal distribution. Then here on a normal distribution, we're going to record this number that we have, 1.48. It's a positive z value, so we're going to have that above the mean, so we're going to have it over here. And then what we're looking for is we're looking to be less than or equal to 1.48. So here we have less than or equal to 1.48. Cool. So now we're looking for this shaded region. So that's our objective, is to find the probability for this shaded region. We're going to look up a z value of 1.48 on our table, and that we got as 0.9306. The last thing that we have to ask ourselves is this. In our table, we're always shading to the left of this cutoff. Right? Oops. Here in our table, we're always shading to the left of the cutoff. In our graph, are we also shading to the left of that cutoff? Yep. So therefore, we know that this is the percentage that we're looking for. Right? What we're going to do here in a little bit is we're not going to be looking for the left of this cutoff. We're going to start to look for stuff to the right of this cutoff. We're still going to look this up in our table, but what are we going to do with this then? Subtract that from 1, right? Does that make sense? Because we have 100% of our distribution. From here on down, we know we have 0.9306. So then if we went from here, what's up, we're just going to take 1 minus 0.9306 to get from 0. But we haven't gotten there yet, but I just want to foreshadow that a little bit. All right, is everybody good with the question A? All right, then let's go on to question B. Probability that z is strictly less than 1.48.
Wouldn't you go to 0.07? Because it has to be less
Wouldn't it be the same because the equation you said was...
Oh, yeah, that's right.
Good. So this right here is going to be equal to 0.9306. Now the reason why it's going to be also equal to 0.9306, just like we had in part A, is because the only thing that we're doing here is we're leaving away the equal sign, right? And then just going back to the discussion that we had last class and at the beginning of this class, the only thing that we're doing is we're leaving away one of these equal signs, but the probability is still the same. A very, very, very common mistake. So what I'm about to show you guys is wrong, right? A very, very common mistake is that people will look up the probability that z is less than or equal to 1.47, right? Saying that, hey, I want to go less than 1.48, so I'm just going to look up. Like, this is absolutely wrong. We know that because we're dealing with a continuous random variable, which is z is a continuous random variable, because we're dealing with a z, that we can leave away this equal sign, and we're still going to end up with the same probability. All right, everybody good with A and B? Okay. Then take a minute for yourself and see if you can do C by yourself.
Does anybody need a little extra time? All right. So we have the probability that z is less than 0.67. Our first step always is to look to see, is this right here a z value? It is a z value, so therefore we know that we're going to be dealing with a normal distribution, a standard normal distribution. The next thing that we're going to do is we're going to annotate our value. It's 0.67, which is a positive number, so we know that we're going to be above the mean. So over here, we're above the mean. And we're looking to be less than 0.67. So again, here to the left of 0.67 is less than 0.67, so we're looking for this right here. Everybody good with the setup? Going through that thought process is very, very, very important because these types of problems are going to become a lot more difficult as we move on. So going through that and identifying exactly what you're trying to find, I always say that if you can visualize it, chances are you're going to get there, right? So here, this is what we're trying to figure out. All right, so now we know that we're trying to go less than 0.67. The next thing that we're going to do is look up 0.67 in our table. First, we're going to go down to one decimal place, which is 0.6, and then over to our second decimal place, which is 0.07. If we look to see where these two things meet up, we get 0.7486. Everybody good with 0.7486? All right, then we looked up 0.7486. Then the last question that we have to ask ourselves is, here we're shading to the left of 0.67. Is that the same direction that we shade on our table? Yep. So therefore, this 0.7486 is what we're looking for. Because here we're shading to the left, and our table also shades to the left. So therefore, the correct answer is 0.7486. Any questions about 0.7486? Everybody's good with this? All right. Then question D. What's the answer to question D? The same thing. Why is it the same thing? Awesome. Doesn't matter whether or not we include the equality or don't include the equality. C did not include it this time, but now D is including it. So, therefore, the probability of exactly one value for a continuous random variable is always going to be 0. So therefore, adding in a probability of 0 doesn't change anything to our numerical answer. All right. Any questions about D? All right. See if you can do E by yourself. Does anybody need a little extra time? All right. So, same thing then. First question that we're going to ask ourselves is this a z value? It is a z value, so therefore we know that we're going to be dealing with a standard normal distribution or a bell-shaped and symmetric distribution. Here now we have a value of negative 2.25. So if we have a z value of negative 2.25, we know that we're going to be below the mean. So here we have a cutoff of negative 2.25, and again, this is a z value. And we're also looking to be less than negative 2.25, so we're looking for this shaded region over here. Everybody good with those first couple of steps? Any questions about those steps? All right. So now we're going to look up a z-value of negative 2.25. If we want to look that up, where are we going to look that one up? On the back side. So if we go to negative 2.25, right? Yep, negative 2.25. Again, we're going to come down here to negative 2.2, and then up to 0.05. So then we can get to negative 2.25, which is 0.0122. Everybody good with finding 0.0122? All right. So then we're going to have 0.0122. What's the last question that we ask ourselves? Are we shading to the left right here? Yes, we are, and that's the same direction that our table shades in, so then therefore this is the probability that we're looking for. How do you guys feel about these problems so far? Pretty good? All right, then let's do F. Take a minute or so for yourself and see if you can do F by yourself. Anybody need a little extra time? All right. All right, so you guys walk me through this one now. What's the first thing that I do? See if it's a Z. We have a Z, so then therefore I can draw what? My bell-shaped curve. Awesome. Here's my bell-shaped curve. What's the next step? Say again? Not quite going to the chart quite yet. I shade on the left side, but where do I shade up until? Good. So first I have to write on here my negative 1.37. Right? So I first have to record negative 1.37, which is just this value right here. And now you're right that I want to be to the left of negative 1.37, right? I want to be less than 1.37. And less than 1.37 is to the left of negative 1.37. So therefore, I'm shading in over here. Good. Everybody good with that stuff so far? All right, now what do I do? Now I go to the chart, right? And I look up at negative 1.37. What do I get for negative 1.37? 0.0853. Which is one that we already looked up earlier today, right? Everybody good with 0.0853? Then what's the last question I asked myself? Yep. Here, did I shade into the left? And I did. And the reason why that's important is because the table also shades in from the left. So therefore, I know that this is the percentage that I'm looking for. Everybody good with this? We are going to do them all. Let's keep going through them. So when I first started teaching this class, I literally taught chapter 5 in a day, right? And I was just like, they're getting it. They know how to look these values up in the table. Like, we're good to go. We did 6 or 7 of these problems. And then I started to notice once we were getting to chapter 7 and chapter 8, the reason why people were struggling with chapter 7 and chapter 8 wasn't because of chapter 7 and chapter 8. It's because of these Z values, right? Looking up these Z values.
To get chapter 5 down, the rest should be
The rest is going to be so much easier. So a lot of the other professors, whenever they teach this class, they go through chapter 5 quick. I, by far, take the most time on chapter 5, and it pays dividends later on in the semester. So yes, so we're going to go through all these, and then by the end of class, you're going to be like, no, please, no more, and then we'll move on, right? So there's a little bit of torture going on today, but it's a good thing, right? All right, see if you can do G by yourself. not a trick question.
Is this where I use
You-
my calculator?
Nope, you don't have to use your calculator for this either. You can do this. We'll take a minute for yourself and then see. We'll do this one together here in a minute. Give it your best shot. All right, does anybody need a little extra time? All right. So the important thing with these problems is, like I said at the beginning when we first started doing them, is try to introduce you guys to this process, follow the process, and it's going to help out. Right? In that process, what's the first question that we ask ourselves? Do we have a z value? And we do have a z value. So therefore, we can do what? Do our bell-shaped curve. Awesome. All right, so now we have our bell-shaped curve. What's the next step that we do? Good. We're going to try to put where negative 4.37 is, and it's a negative number, so therefore it's going to be below the mean. And it's negative 4.37, so I think one of the things that you guys started to realize is that negative 4.37 is like way over here. Right? It's not like negative 1.2 or negative 1.8 or something. That's negative 4.37. So we're really far below. All right. So now we put in our cutoff right there. What's the next step in our process? Good. We're going to figure out which way we're trying to shade. Are we trying to shade above or below negative 4.37? Below negative 4.37 because we want to be less than negative 4.37. So therefore, we're shading in this area over here. What's the next step in our process? Now we go to the table. And now when we go to the table, we're trying to look up negative 4.37. So the way that we would always do this is go to, if we had a z value of negative 4.37, we would go down to the first decimal place, so negative 4.3. But this is where you guys were like, ruh-roh, right? What do I do? Because now this table only goes to negative 3.9. So let's think about this here for a second. If we wanted to keep on going all the way past negative 3.9, right, and keep on going on, and then look up, so we would go to negative 4.3, right, which would be like, I don't know, up here or something like that. And then the next thing that we would do is go over to our second decimal place, which is 0.07, so we would be somewhere over here in this column. But let's look at this table here for a second, right? These numbers right here represented the percentage of the graph that we have shaded in. So let's go to the largest value, or technically it's the smallest value that we can look at in this table, which is negative 3.99. But if we go to negative 3.99 and you shade in from the left, approximately what percentage of the graph have we shaded in? Zero. So that means this. If we go back over here, if we were to shade in all the way up to negative 3.99, what our table is telling us, right? So I think I have a different color. Do I have a different color? I do have a different color. You have a different color too? Right? Colors are great, right? I don't know why I'm always writing in black, because different colors are fun. All right, so I'm going to shade up on top of this one because I used black and you're not going to be able to see the red. But if I shade in all the way up to negative 3.99, then my table will tell me that I've shaded in approximately 0% of the graph. Well, now here's the thing. I'm not going to shade all the way up to 3.99. I'm going to stop short of that. I'm going to stop at negative 4.37. So if here we've shaded in approximately 0% of the graph, then here
we should shade in less than that, right? A smaller percentage than that. So here we're definitely shading in approximately 0% of our graph, right? Here the important thing to note is this. We're only going down to 4 decimal places right here. So if we would have a table that maybe goes down to 6 or 7 or 8 decimal places, over here we might get 0.000001. But then if we go all the way up to negative 4.37 and we follow this over, it might be something like 0.0000000001. But because our table, you guys can't see that last little one, but because we're only going to 4 decimal places, that's why right here the table is giving us the same values. Right? Is everybody good with that? So this is not a trick question. This is just saying that, hey, I want you to start to recognize that all these things right here, we're pretty much shading in 0% of the graph. So that I can give you guys any z value that I want. Remember that the z value is just saying how far you are away from the mean, right? Technically it's the average squared distance, but how far you are away from the mean is a perfectly fine way to conceptualize it. And here, what we're saying is that we've shaded in 0% of the graph. So if we go even farther away, then we're going to have shaded in approximately 0% of the graph as well. All right, so everybody good with this? All right. So therefore, here, the answer to this question, if we look up this percentage in our table, we're going to get that it's approximately 0.0000. And now, that's just looking up that percentage. We always have a final question to ask. And what's that final question that we have to ask? Good. Are we shading in to the left of our cutoff for this problem? And we are. That's the same direction that we're shading in on our table. So therefore, this is the percentage that we're looking for. Everybody good with this? All right. See if you can do H by yourself. Anybody need a little extra time? All right. So again, you guys walk me through this process. What's our first step? Draw the curve, because we have a z value. Here it's a z, so therefore we know that we're going to use our standard normal distribution or bell-shaped and symmetric curve. What's our next step? Good. Find out where our value 5.47 is on the graph. It's positive, so it's above the mean. And now we also have this huge value, which is 5.47. What's our next step that we do? Shade to the left. So here we're going less than 5.47. So we're shading in all of this right here, which is to the left of 5.47. And then what's our next step in the process? Look up 5.47 in our table. But again, what's the issue that we run into? Stops at 3.99. But even at 3.99, approximately what percentage of the graph have we shaded in? 100%. So therefore, if we don't stop at 3.99, if we go all the way up to 5.47, approximately what percentage of the graph have we shaded in? 100%. Or 0.1003. All right, is everybody good with H? You guys get the gist of whenever there's values that aren't on the table, you can still figure out what percentages that we're looking for. All right, see if you can do I by yourself.
Does anybody need a little extra time? Right, then let's go through the process. Process says, check to make sure that this is a z. It is a z, so therefore we can use our standard normal distribution. Then the next thing to do is to record the value that we have here. We have a positive 1.29. Positive 1.29 is going to be above the mean, so here this is also above the mean. Now the next thing in our process is to shade the area that we want, but now we don't want to be less than 1.29. We want to be greater than or equal to 1.29. If we're greater than 1.29, then we're going to the right of 1.29. So therefore, now we're shading in this area over here. Is everybody good with that?
So the or equal to is irrelevant. You just look at what they.
Exactly, right? Again, it doesn't matter whether or not we have equal here, we don't have equal to here. It's always still just going to be the direction of that sign, right? Because by including the equal, we're just including something that has a probability of 0. Okay, so here we're going to the right of 1.29. The next step in our process is to look up 1.29. So if we look up 1.2 and then come over here to 0.09, we get 0.9015. Is everybody good with 0.9015? So then here we get 0.9015. But then, just like I've always been emphasizing for all these other problems, what's the last question we have to ask ourselves? Which way did we shade? And here we're shading to the right. Does our table shade to the right? No. Shades to the left. So what do we have to do here if we want to find the truth?
Subtract it from 1.
Subtract it from 1. Is everybody good with why we're subtracting it from 1? Does that make intuitive sense why we're subtracting from 1? All right. Then we're going to have, so this then we're going to have 1 minus 0.9015. And if you do this arithmetic, you should end up with 0.0985. Everybody good with 0.0985? Yes.
Would it be wrong to just go onto the negative side because this is the same answer?
It would not be wrong, right? But the main thing that I'm trying to introduce you guys to right now is this process, right? I think everybody sees that what we're really doing here isn't like super rocket science. Like I think several of you have worked on to subsequent problems, right? Because like this stuff is pretty easy to you. The first thing that I want to do is get you guys used to this process. If you follow the process, you're going to get these all right. But you're completely correct that you could look up that negative value, and that one would be then this percentage that you're looking at. I'm not going to talk about that until we get to chapter 6. We're going to spend chapter 5 getting used to this stuff first. But then, yes, that's completely fine the way that you did it too. All right, how do you guys feel about these problems so far? All right. Then let's do, why don't we skip these next two? What's going to be the difference in the answer that we get for for J versus K? What's going to be the difference in the answer that we get for J versus K? Nothing. Why is it nothing? One of them has the equal sign and one of them doesn't have the equal sign, right? So I think you guys would be good with finding this out, right? Because the only thing that we're doing here is we're shading to the right, we're not shading to the left, so we would just subtract it from 1 instead of just using it, right? I think everybody's good with it. Let's do these two right here. Let's do L and M, because those are the ones that aren't necessarily on the table. I want to make sure that everybody feels comfortable with those two as well. So take a minute for yourself and see if you can do L by yourself. Does anybody need a little extra time for L? All right, so let's do L. Let's follow the process. Process says, is this right here a Z? It is a Z, so therefore I know I can use my standard normal distribution or my bell-shaped and symmetric curve. Then the next thing that we're going to do is we're going to record this value, 4.28. It's positive, so we know that we're going to be above the mean, 4.28. The next step in the process then is to say, hey, which way are we going to shade? We want to be greater than 4.28. Right, is everybody good that we're looking for greater than 4.28? So we're looking for this area over here. So that's what we're trying to find. Our next step in the process is to look up 4.28 in our table. 4.28 is not in our table, but what's the highest value that we can get in our table? 3.99. If we look up 3.99, what percentage do we get? 100%. So, is this our final answer? No. What do we have to still do? Subtract it from 1, because here we're shading in the opposite direction of our table. Our table gives us what's from here down, from 4.28 down. So therefore, we have to take 1 minus 1.000. So that's going to give us approximately 0%. Everybody good with this? All right. Without even doing that whole process for M, right? What number are we going to get for M? 1, right? Is everybody good with 1? Because negative 6.72 is going to be really, really far to the left. But we're going to go above negative 6.72. So therefore, we're shading in pretty much the entire distribution, right? So therefore, according to our table, the closest that we can get is this is just going to be 2. Everybody good that this should be 1? All right. Then we're going to skip these next 3 because I think you guys are getting the gist of these. Right? Does anybody want to do them? All right. But we're going to do these other ones down here because we're introducing something else. What's the difference between Q and what we've been doing in the previous problems? We have 2 cutoffs, right? Now we don't just have 1 cutoff, we have 2 cutoffs. The process is still the same, right? Let's take a look at what the process says. The process says, do we have a Z value? We do have a Z value, so therefore we can use our standard normal distribution. Then the next step in our process was to record our values. We're recording now both 1.45 and 2.37. So I'll put so they're both above the mean because they're both positive. I'll put 1.45 right here, and I'll put 2.37 right there. And now what we're trying to do is we're trying to find the Z values that are greater than 1.45, but less than 2.37. So if I wanted to shade this in, where am I going to shade? In between those two, right? I want to go above 1.45, but less than 2.37. So I'm trying to shade in that in-between area. All right, so let's do that. What was our next step in the process? Look at the chart. So now we have to look up 2 numbers in the chart. If we look up 1.45, what do we get? 0.9265. Is everybody good with 0.9265? So that means that from here down, right, because our table is always giving us what's shaded to the left, from here down, we have 0.9265. Everybody good with that? All right. Then if we look up 2.37, what do we get?
0.9911.
Everybody good with 0.9911? And what's that saying? That says from 2.37 down, we have 0.9911 of our distribution. Right? Is everybody good with that? Now, I think that we have this. We shade in or we draw this graph like this, and we want to find the shaded region. What are we going to do?
Subtract 0.9265 from that.
Good. We're going to subtract the smaller one from the larger one in order to get what's in between here. All right? Does that make sense? All right. So then what we're going to do is we're going to take 0.9911 and subtract 0.9265 from it. Okay, 74360. Did I get that right? 0.0646? Yes. Nailed it. Get to keep my job for another day. Right? Is everybody good with what we're doing up here? So, just because we have two cutoffs doesn't mean that we're really doing a whole lot different. Because our process was still, do we have a z-value? Yes, so we have this graph. We still recorded these two values, 1.45 and 2.37 over here. And we still determined which way we were going to shade based off of our symbols. We wanted to be above, right? We want to be above 1.45, but we want to be below 2.37. Therefore, we decided that we want to have this region right here shaded in. And now what we always did is we always looked up these values in our table, 1.45 and 2.37, and now we got these two percentages. And we already know that the percentage that we're getting in our table is always what's shaded to the left. So now what I'm simply just doing is I'm saying, hey, from here on down, we have 0.9265. And from here down, from a z-value of 2.37 down, we have 0.9911. So if we want to find out what's in between here, we're just going to subtract the smaller from the larger, and that's going to give us our shaded region. Is everybody good with this? All right. Then take a minute for yourself and see if you can do R by yourself. Does anybody need a little extra time? All right, let's do this one together. All right, so following the process, our first step is always to verify that this right here is a z. It is a z, so therefore we can use our standard normal distribution. Then the next thing that we do is we record these two values of 0.69, which is above the mean since it's positive, and 1.78, which is also going to be above the mean because it's also positive. They're z values. And now what we want to do is we want to be greater than 0.69 but less than 1.78. So where are we going to shade on this graph? In between them. So again, for this problem, we're in between them. All right, so we're in between them. So now what we're going to do is the next step is we recorded these two values. Now we're going to look these two values up in our table. If you look up 0.69, what percentage do you get? 0.75. What is it? 0.7549. So from here on down, we have 0.7549 of our graph. And if we look up a z-value of 1.78, what percentage do we get here? 9625. Everybody good with these? All right. And then in order to find what's in between, we're going to subtract the smaller one from the larger one. So we're going to have 0.9625 minus 0.7549. And this is going to give us 0.2076. Awesome. Thank you. Everybody good with 0.2076? You guys get the gist of these problems? All right. So let's, we still have a couple of minutes. So let's just take a glance at these next problems. And we're going to definitely work on these a little bit as well. But if we look at these here, what's just a main difference between what we did right here in R and what we're doing right here in S? The equal sign, right? Does the equal sign make any difference whatsoever? Does everybody feel confident that they would be able to do S by themselves? You guys get the gist? So we're going to skip this one too. All right, then what's the difference between that and T? The negative Z value, right? So we are going to do this one. We're going to do a couple of these at the beginning of next class. But really, what's the main difference going to be?
That's on the backside.
Exactly. We're going to have some cutoff that's now below the mean, right, because it's a negative Z value. We're going to look up that percentage on the backside. We're going to have some small percentage, but then ultimately we're still trying to go above negative 1.8, but below 1.21. So we're still shading in between. So all we're doing is we're just subtracting a smaller percentage, but the process is still the same. So what this is really just trying to get you guys to understand is that having a negative Z value doesn't really make any difference to the process. We're just looking up our numbers a little bit different. But we'll practice these nevertheless. But we're out of time for today, so we'll call it quits there.